So I'm Ville Virtanen and I'm from the University of Helsinki. And I'm going to talk about what we have learned by using Magma Chamber Simulator about the assimilation process in the Duluth Complex and what it has revealed about the sulphide saturation in the Duluth. And this study has been done in collaboration with Jussi Heinonen, also from the University of Helsinki, and Nicholas Barber from the University of Cambridge. So first of all, what is Magma Chamber Simulator? It's a thermodynamically constrained geochemical modeling tool, and it's especially designed for open magmatic processes. So how does it work? First of all, we have MELTS engine for magma for modeling the fractional crystallization. Then there is another MELTS engine for the wall rock to model the phase equilibrium in the wall rock, as well as the partial melting. And then there are another MELTS engine for the recharged magmas, but we are not concentrating on these today. In addition to the phase equilibrium, the Magma Chamber Simulator keeps track on major and trace elements of all of these subsystems. And also isotopes can be modeled as well. So let's move to the Duluth Complex, which is the case study. Let's put the pointer. Okay, so it's located in northeastern Minnesota, and it's a multi-stage layered intrusion with this green color here. And it hosts nickel copper deposits at the footwall zone. And most of these deposits are hosted by the troctolites, but some of them close to the Virginia Formation are hosted by norites. So these norites are present adjacent to the black shale footwall, as well as the black shale xenoliths. And the Virginia Formation has been shown to be the major source for sulfur in these mineralizations. So before modeling assimilation, we wanted to try fractional crystallization models to see if we can form these troctolithic intrusions. And we took the parental magma composition from these cogenetic basalts, and we applied the pressure of 2 kilobars. And then we tested different water contents between dry and 2.25 weight% water. And this is the intrusion that we tried to model, the Partridge River intrusion. So here's a natural cumulate sequence from that same intrusion. And it starts with melatroctolite at the bottom, followed by a thicker troctolite. And then it ends up with anorthositic troctolite on top. And this is the typical sequence for a single magmatic pulse in the Duluth complex. And something to point out here is that all of the rock types are troctolithic, so they are olivine plagioclase cumulates. And this stratigraphical sequence comes from a place where there is no copper nickel sulfide deposit. So then let's look at our modeled sequences. With the dry magma, we first form a thin anorthosite, followed by a troctolite, and then a thick gabbro. And because of this thick gabbro, so clinopyroxene-rich rock, it's not applicable to the natural case. Then when we added 0.14 weight% water, it's about the same case. There's also a thick gabbro here. Then with 1 weight% of water, we get a dramatic increase in olivine-rich rock types. So we form first a dunite here, followed by a troctolite, olivine gabbros, then gabbros, and another layer of troctolite up there. And in the most water-rich model, we form anorthositic troctolite on top instead of gabbro and troctolite, but otherwise the same with the 1 weight% water. So based on these models, we chose the parental melt with 1 weight% of water for our AFC models. And these models were done in order to try to model the norite-hosted copper-nickel deposits. And for the wall rock, we chose the Virginia Formation black shale, which is the main source of sulfur in the mineralizations. So here's a Magma Chamber Simulator visualizer tool. And soon I will be showing you a video with this, but first I would like to point out that this model starts with magma at liquidus conditions, so 1225 degrees Celsius, and the wall rock has been preheated to 600 degrees, and that the magma mass at the beginning of the model is 100 grams. And the melt can be seen below at the bottom section, and the wall rock evolution on the top here. So when the fractional crystallization begins, the magma starts losing heat, which goes to the wall rock. And before we go to the actual assimilation, I'd like to point out that we have now formed a thin dunite followed by a troctolithic cumulate on top of it. On top here, you can see various colors representing different minerals in the wall rock. We will not go in details in that, but I'd like to point out that there is now partial melt present in the wall rock. Now let's see what happens when the wall rock starts to partially melt and the assimilation begins. So you see that the wall rock is decreasing in size as the assimilation goes on. And now the model stops because the wall rock temperature is at 1000 degrees and the magma temperature is only slightly above that. So the magma doesn't have any more heat energy to melt the wall rock any further. So the maximum amount of assimilation in this model is 38 grams to the magma. And consequently, because there is assimilation, there is first the troctolites, but then when the assimilation surpasses about 20 grams, there is noritic cumulates forming. So let's move to the SCSS results. So sulfur content at sulphide saturation. We used the model of Smythe et al. 2017. On the y-axis, you can see sulfur concentration in parts per million. And on the x-axis, you can see cumulate mass in the magma system. And this solid black line here shows the sulfur content at sulphide saturation in the fractional crystallizing Duluth magma. And this stippled black line here is sulfur content in melt. And we started with 800 parts per million in the melt. So with this model, we reached the sulphide saturation when about 27% of the magma has solidified, and the temperature is 1145 degrees Celsius. Then if we look at the sulphide saturation curve in the AFC model, we see that as soon as the AFC begins here, the SCSS drops dramatically. And why does this happen? Here's the main reason. So on the y-axis, there's weight percent of element, oxide, and cumulate mass again on the x-axis. So in the fractional crystallization, the iron oxide in melt is here on the black line. And we see as soon as the assimilation starts, the iron oxide content starts to drop in the melt. And this lowers effectively the SCSS. Another important feature is that in the assimilation model, because the wall rock is hydrous, the water content of the melt increases, which also lowers the SCSS. So let's move to the sulfur part of this model. So we modeled the sulfur with the trace element tool of the Magma Chamber Simulator, but here's the first model without any sulfur in the wall rock. So we see that the sulfate saturation in this model occurs at when 13% of the magma has solidified and the temperature is 1140 degrees Celsius. And this is, in terms of solidification, before the fractional crystallization model. But then we see that because there is no addition of sulfur from the wall rock to the magma, the sulfur content in the melt increases slower than in the fractional crystallization model. So because of this, the overall sulfides that saturate from the magma is slower than in the fractional crystallization model. Then we added 6,000 ppm of sulfur to the wall rock black shale. And this is actually the average sulfur content in the wall rock black shale in Virginia Formation. And in this first trace element model, we modeled sulfur as a compatible element. So this would roughly correspond, let's say that we have pyrrhotite in the wall rock and it's not melting because the temperature is too low and it stays in the residual wall rock. So the sulfur content in melt is almost same as in the sulfur-free wall rock. And at the highest point, the amount of black shale sulfur in the melt is only 6% of the total sulfur. Then we decreased the partition coefficient. So now sulfur is as compatible to the partial melt as in the wall rock residual. So here we see that as soon as the assimilation begins, there is a dramatic increase of sulfur in the magma melt system. And the sulfide saturation takes place when 8% of the magma has solidified. And at this point, the temperature is 1150 degrees Celsius. And at the highest point here, when all the assimilation has occurred, there is 74% of black shale derived sulfur of the total sulfur in the melt. Then we also modeled the sulfur as completely incompatible element in the wall rock. So in this case, there should be some sort of a process that completely leaches the sulfur and transports it to the magma. And here there is even more dramatic increase in sulfur early on during the assimilation. And here the sulfide saturation takes place when 5% of the magma has solidified and the temperature is about 1150 degrees Celsius. And in this model, when all the assimilation has occurred, about 79% of the sulfur in the melt has derived from the black shale. And something to point out here is that the monosulfide solid solution solidus is about 1190 degrees Celsius. So in any of these models, sulfide melt cannot form in the magma, not in the fractional crystallization nor in the AFC models. But I'd just like to say that this has been done now with the pure FES system and might be slightly different when we add copper and nickel to the mixture. So to conclude this up, norites in the Duluth complex require about 20 to 30% assimilation. So these rocks that you can see here. Troctolite formation is probably dominated by fractional crystallization without assimilation from the wall rock, or not assimilation of silicates from the wall rock. So maybe there could be another way of getting sulfur from the black shale to the magma without changing the silicate composition. And maybe the hydrous magma that is required for the troctolites or for the olivine-rich cumulates is a clue that there could be fluids coming from the wall rock to the magma. But we will have to see that in more detail. Also, assimilation effectively lowers the sulfide SCSS, but at the same time, it increases the amount of melt mass, so it lowers the overall sulfur content in the melt if the wall rock is not containing any sulfur or no sulfur is coming from the wall rock to the magma. Previous sulfur isotopic evidence indicates that 75% of the sulfur within the Duluth Complex deposits comes from the adjacent black shale. And this is compatible with our AFC models, where the partition coefficient of sulfur is about 1 or below that in the wall rock. And lastly, the magma temperature is too low for formation of extensive sulphide melt. Thank you.